We will now start a new chapter. So we are going to study weak and weak star topologies. So up to now we have been dealing with the norm topology. So this is a metric topology. So now we want to study other kinds of topologies on a Banach space, and these have a lot of very nice applications. Okay, so we will start defining. So first we will study the weak topology. So let V be Banach. The weak topology on V is the coarsest that is smallest topology such that f is continuous for every f in V star. Okay, so we are going to economize on the number of open sets. When I say smallest topology, I mean the least number of open sets possible, so that the members of the dual space are still continuous. Okay, so open respectively closed sets in this topology are called weakly open, similarly weakly closed. Okay, so how do you construct such a topology? So this is well known in topology, how to construct, given a set and a set of mappings f from X to a topological space Y, Fi. So then I in some indexing set I, what is the smallest topology such that all these X's are continuous. So if U is open in Y, then Fi inverse of U must be open in X, and then every open set in the topology here must contain all finite intersections of these and all arbitrary unions of finite intersections of these. So that is how the topology on X is constructed. Okay, so therefore basic open neighborhood. So what is here, we are taking Y equals R. So we have F in V star. So F goes from V to R or C, it's whatever I am saying for R works for C also. So we want every what's the neighborhood here? So if I take neighborhood, so if I take x naught, then x naught goes to f of x naught. So we will take a neighborhood f of x naught minus epsilon, f of x naught plus epsilon, and you all inverse images of this should be open, and then you must take finite intersection of such sets, and therefore that will constitute a basic neighborhood system for at each point, and then from this you can construct the rest of the open sets. So the basic neighborhood system for x naught in V in the weak topology is the collection of all sets of the form. Okay, so U will be set of all x in V such that x f of x should belong to this thing. and therefore mod fi of x minus x naught is less than epsilon for all I in I, where fi I in I is a finite collection of elements of V star. So when I want to take finite intersection of sets of this form, I would take finite number of functionals and then take the inverse image of all that and take the intersection. So this should be true for all I in I, and so this is forms a neighborhood system for this. So given any point x naught, a typical neighborhood in the weak topology will look like this. So first proposition, the weak topology is Hausdorff. So it is important because when we defined even a topological vector space, we always wanted the topology to be Hausdorff. So let us take xy in V. So we want to have disjoint neighborhoods. Therefore, V star separates points implies there exists an f in V star such that fx is not equal to f of y. So let us take U neighborhood of fx and V neighborhood of fy in R or C or whichever you want, and then U intersection V is empty because real line or complex plane is Hausdorff anyway, and therefore you can always find this. And therefore if you take f inverse U, x belongs to this, and f inverse V, y belongs to this, and f inverse U intersection f inverse V will be empty, and these are all open, weakly open. This is also weakly open because U and V are open and f is continuous in the weak topology, and therefore these are weakly open. So this proves, so given any point I found two disjoint neighborhoods, and therefore you have this. Okay, so notation. So xn, a sequence in V. So if xn goes to x in norm topology, what do you mean? That is xn minus x tends to 0 as n tends to infinity, then we write xn goes to x. If xn converges to x in the weak topology, so we call it weakly convergent, then we write xn with a half arrow like this, xn weakly converges to x. Okay. So now we have another proposition. Okay. V Banach and xn a sequence in V. 1. xn converges to x weakly if and only if f of xn converges to f of x. This is in the real line or complex plane for every f in V star. 2. xn converges to x in norm implies it converges weakly as well. So norm topology is stronger. 3. If xn converges to x weakly, then norm xn is bounded and norm x is less than or equal to lim inf n tending to infinity norm xn. And then 4, we have if xn goes weakly to x and fn converges to f in V star, so this in V, then f of xn, fn xn goes to f of x. So you have, remember, you have two in a sequences here. So if one is strong and the other is weak, then the limit will be the correct one. Okay, so then, so proof. So 1. So xn goes to x weakly, then by definition, since all the f's are continuous for this topology, f of xn has to converge to f of x. So now let us assume that f of xn converges to f of x for every f in V star. Then how does a neighborhood of x look like? So U is a neighborhood of x, if you remember. This is all y in V such that mod fi of x minus y is less than epsilon for all I in I, and I is finite and fi of course belongs to V star. So this is how a neighborhood would look like. Now if fnx converges to f of x, then for every I you have, there exists a ni such that n greater or equal to ni implies fnx, fi of xn minus fi of x is less than epsilon, because you have fnx converges to f of x for every f in V star. Now you take n to be the maximum of the ni's, I is a finite set, you can take that, and therefore for all n greater or equal to n you have that xn belongs to U. So after some time the sequence belongs to any neighborhood, and therefore so this implies that xn converges to x. So given any weak neighborhood of x, you have that after n you have xn belongs to U, and that is precisely the definition of convergence. Okay. 2. So xn converges to x, so implies for every f in V star we have f of xn converges to f of x, and this implies by 1 you have that xn converges to x weakly. Third, okay, so xn converges to x in V, that means for every x, for every f in V star we have fn xn, f of xn converges to f of x, that is jxn of f converges to jx of f, and this implies that by the uniform boundedness principle we have that norm jxn is less than or equal to c, that is norm xn is less than or equal to c. So this shows that the sequence is bounded. Then we also showed when you have a sequence in which you have every point converges, then the limit transformation satisfies this condition. So you have and norm xn, norm x is less than or equal to lim inf norm xn, already proved. Uniform boundedness chapter, we have already seen this proof. And fourth one, so we have xn goes weakly and fn goes to f, in norm in V star. So we want f of xn, fn xn minus f of x. This is less than or equal to mod fn xn minus fn of x, minus f of xn plus mod f of xn minus f of x. The first one is less than or equal to norm fn minus f times norm xn plus mod f of xn minus f of x. Now by the first part of this proposition, this goes to 0 since xn goes to x weakly, and then this goes to 0 and this is bounded by the part 3, and therefore you have the whole thing goes to 0 and we have what we want. Okay. So this proves this proposition completely. So now let's look at an example. You look at little l2. So this is a set of all square summable sequences with the corresponding norm, and then you have that L2 star is identified with L2 in the usual way. Okay. So now you look at En to be equal to 0 etc., 1 in the nth place, 0 elsewhere. Take the sequence, this belongs to little l2, norm En in L2 is 1. Okay. So now if you take any x in L2, then you look at x En, or rather take this as L2 star. Okay, so x En, and that's equal to xn. But then what do you know about x? X is in L2, so sigma xn square is finite. So this implies that xn goes to 0. Therefore xen goes to 0 for every x in L2, which is the dual space, and therefore you have that En converges weakly to 0. If for every linear functional xen goes to 0, and therefore En converges weakly to 0. But remember that norm En minus Em is square root of 2, and therefore En has no Cauchy subsequence in norm. Therefore, for no subsequence En will converge in norm, and therefore we know that norm convergence implies weak convergence, but the converse is not true. Weak convergence does not imply norm convergence. Proposition: V finite dimensional, then the norm and weak topologies coincide. So there is no difference. So if anything is interesting, it is only in infinite dimensions. Okay. So proof. Okay, so weak topology, weakly open implies norm open, because the norm topology is much bigger, weak topology is a smaller topology, so every element of the weak topology is a member of the norm topology. So now let us take U be open in norm topology. So let x naught belong to U, and let us then implies there exists an R positive such that the ball center x naught and radius R is still contained in U. Okay. So let us assume dimension of V equal to n, and then V1 Vn is a basis for V, and without loss of generality we can assume norm Vi equal to 1 for all 1 less than equal to I less than equal to n. Okay. So then Fi, okay, so any x can be written as sigma xi Vi, I equals 1 to n, and so you take Fi of x equals xi. So projection to the ith coordinate. So then these are all continuous linear functionals. Okay. So then you have norm of x minus x naught is equal to norm sigma I equals 1 to n Fi of x minus x naught into Vi. So that is how the projections have been defined. That's equal to less than equal to sigma I equals 1 to n mod Fi of x minus x naught. Okay. So now you take W equal to set of all x in B such that mod Fi of x minus x naught is less than R by n, 1 less than equal to I less than equal to n. So then W is weakly open. This is a typical neighborhood of x naught. X naught belongs to W and W is weakly open, and then if all of these are less than R by n, then you have, and if x belongs to W, we have norm of x minus x naught is less than R, and therefore W is contained in B of x naught R, and x naught belongs to it. So B of x naught R contains a weak neighborhood of every point in it, implies, which is of course contained in U, implies U is weakly open, because every point in it contains a weak neighborhood inside the same set, and therefore every norm open set is weakly open, every weak open is norm open, therefore the two topologies are one and the same. So we only want to, if at all there is going to be a difference, we have it only in infinite dimensions.